Hello everyone, welcome to the talk. I think the presentation is...
No, that's just a wall. It's on the
okay.
TVs.
Okay, okay, cool. Welcome to the talk. I'm Ankur from the data platform team at Apple.
I'm Rehan. I work with Ankur at Apple on the Apple Ray Data Platform team.
Hey everyone, I'm Deepak from the Apple Ray team.
Cool, let's start this session with three key dimensions. First being the GenAI landscape. As we saw in the keynote, it's being evolving very rapidly. We see large-scale acceleration of AI development.
I think the mic isn't picking you up.
Is happening as we speak. Agents, inference, tuning, and training have become a household name just in a few years. Can't hear that?
Hello?
Hello. Is it working, this one? Yeah. Okay, I'll just use this one then.
Oh, no, it is working. Just really soft.
Okay. Cool. So I'll just start again. So we have a large-scale acceleration of AI development happening at a very fast pace lately. We see agent inference tuning, training, and data becoming household name in just a few years. There is a need for governed, reliable access of OSS models, and this is still an active topic of research. To complement this, we have a very vibrant OSS community. We see that the vLLM Ray community is thriving, and we see new model families getting released every now and then. And finally, we have a very robust platform provided by Ray infrastructure. It provides a common ground for diverse ML workloads. It also paves the foundation for compliant, performant, and reliable model hosting for OSS models. Keeping these three challenges in mind, let's see what challenges and requirements an enterprise faces when it comes to OSS model hosting. First being the seamless access. Given the diverse set of users at enterprise, easy discovery, reuse, and ease of onboarding of OSS model is critical for success. Next being the governance should be simplified. Consistent, compliant, and robust access control is what build trust in the platform and reduce a lot of overhead from the user to make sure the models are used in the right fashion for the right use cases. Next is the performance. To onboard any production use case, performance and reliability is critical. As we talked about earlier, new models are getting released at a very fast pace. We need robust tooling for rapid model rollout, upgrades, and to keep up with the pace of the industry. And finally, the system needs to remain cost-effective to be viable. We believe that vLLM and RayServe provides a very compelling solution for these challenges. Let's see how it fits in the whole broader picture. The broader ML community is Python-friendly, and vLLM and RayServe both are Python native, focusing on models and workflows. Next, they integrate very well among each other. vLLM is provided as a first-class support on the Ray platform, providing seamless scaling and orchestration of inferencing. The vLLM community is very vibrant. It delivers latest innovation and best practices at the speed of light. And finally, the release velocities of these platforms is very good, and it provides day zero support for all the latest innovation without friction. With these key considerations, we feel that vLLM and RayServe provides a very good, robust platform for providing OSS model hosting at an enterprise scale. I'll hand it over to Deepak to share more about how to build a platform, production-grade platform using vLLM and Ray. Over to you, Deepak.
Thank you, Ankur. Right. So I'm going to walk you through a few different perspectives that we need to think when we build a production-grade open source model hosting stack. The first one is thinking from a user journey perspective. It's very important to have a well-defined, compliant access for OSS models from a user perspective. Starts with a unified discovery. Often when you're building an application, it's AI app or agentic, you would be exploring for models, searching for models in different places. It's important to have a single pane view so you can search, explore, and identify the models that fit your use case. And once you've identified the model, most often in large-scale enterprise, you have to go through an approval process, right? And here, having a streamlined approval process ensures we are able to meet, open source terms of use when we are using the model in system. And then comes pulling the model weights and then providing governance on top of it. Having a well-defined path that can help you download the models and put it in a governed storage helps us meet few different things. We can be compliant, enable traceability and auditing of usage. And last but not least, when you think about converting a model weight into a really scalable endpoint, from user perspective, all they care for is having access to an endpoint that they can work with and integrate. But from infra perspective, autoscaling, security, and many other things like cost observability are all implicit. So we need to have capabilities for those. I'll flip the page to see a different perspective here. This is the model lifecycle management. Generally, new models, as I said before, enter our environment through a well-defined path. In our ecosystem, we use Ray jobs to download models and maybe have transformations if we need to quantize and so on. And once we have these model weights pulled into a governed storage, we have a low-code framework built on top of vLLM and Ray serve. And this helps us turn model weights into a quick one-click deployment. Once the models are up and running, there are a few different capabilities that we have created, which is required in the lifecycle of a model. Often we see existing models have new weights released in open source. We have to have a strategy to pull the model weights and then make in-place upgrades. Apart from that, we've also seen that over a period of time, tiering is really helpful. I'll cover a bit about that in the upcoming slide. And as I said before, when we have different model endpoints stood up and exposed to multiple tenancies in an enterprise, we need access management, ability to show cost and observability. Not all models last forever. There is always a life cycle involved, and many times usage fizzles. There is a growing interest and there is a plateau, and then sometimes the models don't get usage, so we decommission those. And also, many times we have better models with better capabilities that we need to deploy in favor of old models. Talked about tiering. Let's cover what tiering means here. So we have two types of tiering in our environment, tier 1 and tier 0. So tier 1 is generally research or experimental models. These have very low usage, or maybe they're very early stage deployment. Generally, we have use cases such as research, batch inference, or data generation going on these. And as I said, if the usage fizzles, we tend to retire them. But they also get promoted to tier 0. Whenever there is a tenant who realizes that this is a critical model for their application. So we promote to tier 0. So tier 0 is basically very large models, or those that have very high sustained usage. They're generally serving very latency and SLA sensitive workloads. Because of these reasons, we have benchmarked them. We have some published metrics. This provides guarantees for our customers to rely on. And again, there is also a life cycle involved here. Sometimes the customers prefer to adopt a new model, then we go through tiering and then demote them to tier 1. So far, we've seen user journey, model lifecycle, and also tiering. When you think about deployment strategy and hosting them, in our case, we have two strategies. We have a multi-tenancy strategy where we put tier 1 models to a multi-tenant deployment mode. Basically, this means these models are scaled down to 0. We have optimized for cost, and the trade-off is cold start. But this is reasonable considering these are very early stage models and non-SLA bound. And as we see a ramp up in the usage, we take strategies to move them to tier 0 and also turn them into single tenant deployments. So in this case, single tenant deployment basically means providing some guarantees and making sure we have good SLIs and SLA. These are basically model endpoints that have been provisioned for a single user or a bunch of customers, and they have a provision throughput. As you can see in this picture, an example is having maybe 2 replicas of a model endpoint, which is guaranteed for our customer, and they scale out horizontally as traffic arrives. Okay, so we've seen a lot of strategies around tiering deployment, but also it brings governance into perspective. One of the aspects is having a very good capability to administer these endpoints, which means ability to deploy, update, or retire models. So we have to have a unified UI or API, which we can rely on to basically manage the model lifecycle. And if we think about multi-tenancy, it adds few other responsibilities. We have to have some sort of security for authentication, authorization, and also with that, maybe some level of rate limiting, because we need to provide fair share of resource quotas as well for our customers. When we add these into the equation, it adds overhead, latency, and other sorts of reliability problems. So we introduce caching that can help us, keep the performance and scalability and fault tolerance in place. The last one is observability. I think the common theme I've seen in multiple talks is having a good observability story along with other capabilities. This means having logs, traces, metrics from all the layers of the infrastructure. In this case, it includes vLLM. So we receive metrics, telemetry from multiple different layers, from Kubernetes, from Ray cluster, from vLLM engine. We aggregate all of them in one place so that we can provide different perspectives for users, for infra providers, for operators. With that, I'm going to hand over to Rehan, who will take us through all the interesting aspects of these metrics.
Thank you, Deepak. So, as Deepak mentioned, observability is a key requirement for any production-grade model serving platform. When we think about observability, there are 4 key flavors of metrics that we want to monitor. The first is token metrics, which allow us to track per model usage. These are critical for quota management and billing, as well as to better understand model scaling and traffic requirements. API metrics, like time to first token, throughput, and end-to-end latency, like you get from vLLM, are critical for characterizing model performance in order to define and guarantee SLAs for customers. Rate limits are key because they allow you to identify quota breaches and ensure that bursty traffic from one customer does not degrade quality of service for other customers. Lastly, as you'd expect, error rates are important because they allow you to identify, diagnose, and debug system outages, as well as work to prevent future system outages. Once you begin to track these flavors of metrics, you get a feel for the overall traffic patterns to your service, both on a finer-grained per model level and on a coarser-grained system-wide level. You can begin to explore autoscaling. When considering autoscaling, there are 3 key axes: model loading, model transfer, and idle GPU hours. Faster model loading decreases the cold start time for model replicas, which becomes increasingly critical as you attempt to scale up models in response to heavy bursts of traffic. Parallel model download techniques can take the time it takes to load model weights from cold storage down by about 2,800%. Model transfer refers to the time it takes to transfer model weights across different mediums of memory. Caching weights near or even on device using techniques like network file systems can reduce the time it takes to transfer model weights by up to 53% by avoiding costly network round trips. This one I'm sure everyone's familiar with, idle GPU hours. As model hardware requirements grow and latency SLAs shrink, idle GPU hours become increasingly costly. Scaling model replicas down to 0 allows you to avoid wasting expensive rented hardware, provided you can scale replicas back up quickly enough in response to traffic. Intelligent downscaling rules allow you to scale down model replicas in a matter of minutes, rather than hours as before, allowing you to avoid wasting expensive hardware with little to no utilization. But, as Ankur said, the field of GenAI is rapidly evolving, and systems and platforms built for GenAI also have to evolve and incorporate new techniques in order to keep up with the growing demand. So let's take a little peek at the path ahead. Improvements in scaling elasticity, like autoscaling improvements and model streaming, allow for sub-minute model replica traffic, which enables more responsive scale down and scale up in response to bursts of traffic. Model multiplexing and smarter GPU utilization orchestration allow you to serve better and larger LLMs with fewer GPUs. While performance and reliability improvements like latency tuning and batch scheduling allow you to get more performance from the LLMs you do serve. Lastly, as we mentioned, integrated cost observability dashboards and real-time token-to-cost mappings allow you to provide a transparent billing paradigm for customers, all working together to create the best end user experience. So, as we close out this talk, I'd like to invite you to think about all the other ways in which the field of GenAI and systems for GenAI are continuing to evolve in order to create a more cohesive and better experience for users. Thank you.
All right. We don't have enough microphones for the audience, so I'm going to ask people to...
We can unmic, because I don't think these are working.
Oh, okay.
Yeah.
But for people to ask their questions, sure. If you want to ask questions, please meet over here at the side of the stage and ask the speakers. And then the next event is going to be at 3:15.